We all know what a mirror does, right? You look at yourself, you see yourself, you wave your right hand, and the person in the mirror waves their left hand. Simple stuff. But here's the thing. When you start to think about it carefully, really carefully, the way a scientist has to think about things, you discover something absolutely remarkable about the universe we live in. You discover that the universe is not quite the same as its mirror image. And that's a very strange thing to discover. Let me put it to you this way. Suppose you're talking to someone very far away. I don't mean your friend down the street. I mean someone really far away. Maybe on another planet, circling another star. You can't see them, they can't see you. You're just talking back and forth, maybe by radio waves, and you want to explain to them what you mean by left and right. Now you might think, oh, that's easy. I'll just tell them to look at some star constellation. But no, they're so far away, they see completely different stars than we do. You might say, well, I'll describe a human being and tell them the heart is on the left side. But then they say, what do you mean by left? You're stuck. You see, for a very long time, I'm talking about hundreds of years, physicists believed that there was absolutely no way to do this. We believed that the laws of nature, the fundamental laws of physics, were exactly the same if you looked at them in a mirror, that everything worked the same way whether you called something left or right. This seemed very reasonable. After all, why should the universe care which direction you choose to call left? Think about a clock, a beautiful mechanical clock with gears and springs and all sorts of wonderful machinery inside. Now imagine you build another clock that's exactly like the first one looks in a mirror. Every screw that turns clockwise in the first clock turns counterclockwise in the second one. Every marking that says 2 on one clock says something that looks backwards on the other. You wind them both up the same way, relatively speaking, and you start them going. What happens? Well, they both tick away just fine. They both keep time. The mirror image clock works just as well as the regular clock. All the forces, the spring forces, the friction forces, gravity, all of these obey the same laws whether you're looking at the regular clock or the mirror image clock. This is what we mean by reflection symmetry, or parity conservation if you want to use the fancy physics term. And this seemed to work for everything. Throw a ball, look at it in a mirror. The mirror image ball follows exactly the laws of motion that Newton told us about. Spin a top, shoot light through a lens, run electricity through a wire. Everything worked the same way in the mirror. Electromagnetism, gravity, the forces that hold atoms together, all these forces couldn't tell the difference between left and right, so we were stuck. There seemed to be no way to tell our distant alien friend which way was left without actually sending them something they could look at or hold. You couldn't do it just by describing physics experiments, because all the experiments worked the same way, whether you called one direction left or the other direction left. But then in 1956, two very smart fellows, T.D. Lee and Chien-Shiung, looked at this problem from a different angle. They were thinking about certain peculiar particles that were being discovered in the new particle accelerators. These particles were decaying in strange ways, and there was a puzzle about them. Lee and Yang did something very bold. They said, wait a minute, has anybody actually checked whether parity is conserved in the weak nuclear force, the force that causes radioactive decay? And when they looked at all the experiments that had been done, they found something amazing. Nobody had checked. Everyone just assumed it worked the same way as all the other forces. So they said, why don't we test it? Now, I should tell you, when Lee and Yang first proposed this, a lot of physicists thought it was crazy. Wolfgang Pauli, one of the great pioneers of quantum mechanics, called the idea complete nonsense. I myself thought it was very unlikely. In fact, I was so sure that parity would be conserved that I made a $50 bet against it, which I lost. And I was very happy to lose that bet, because what happened next was extraordinary. A wonderful physicist named Chien-Shiung Wu took up the challenge. She designed a very clever experiment using cobalt-60, which is a radioactive isotope. Now, cobalt-60 nuclei are spinning. They have what we call nuclear spin, like little tops spinning around. What Wu and her team did was get these nuclei very, very cold, close to absolute zero, and then put them in a strong magnetic field so that all the nuclei were spinning in the same direction, like an army of tiny tops, all spinning the same way. Then they watched what happened when these nuclei decayed. They shot out electrons, beta particles we call them. And here's the remarkable thing. The electrons didn't come out equally in all directions. Most of them came out in one particular direction relative to the spin of the nucleus. They came out opposite to the direction of the nuclear spin. Now, why is this so shocking? Look at it this way. Imagine you've got a nucleus spinning this way, and electrons are coming out mostly down. Now, look at that same setup in a mirror. In the mirror, the nucleus is still spinning, but now it's spinning the opposite way. That's what happens to spinning things in mirrors. And the electrons are still coming out in the same direction relative to the mirror. But here's the key point. If the real nucleus has most electrons coming out opposite to the spin direction, then in the mirror the electrons should also be coming out opposite to the spin direction. But the spin direction is reversed in the mirror. So in the mirror, most of the electrons should come out in the opposite direction compared to the real experiment. You build the actual mirror image experiment. You set up the nuclei spinning the opposite way, and you find that, yes, indeed, the electrons come out the other direction. The mirror image experiment gives you different results than the original experiment. Nature can tell the difference between left and right. This is like finding tiny hairs growing on the North Pole of a magnet, but not on the South Pole. It's like discovering that the universe has a handedness built right into it at the most fundamental level. So now, finally, you can tell your alien friend which direction is left. You say, take some cobalt-60, cool it down to nearly absolute zero, put it in a magnetic field so all the nuclei line up and spin in the same direction as the current in your magnetic coil. Watch where the electrons come out. Most of them will come out in one direction. We call that direction down. Now, if you look at your spinning nuclei from the side, they're rotating. One direction of rotation we call clockwise. The other direction we call counterclockwise. Using these directions, you can define left and right the same way we do. There's just one little problem, and this is where it gets really interesting. What if your alien friend is made of antimatter? Now, antimatter is real stuff. For every particle we know, electrons, protons, and so on, there's an antiparticle, an anti-electron, which we call a positron, an antiproton. These antiparticles have the opposite electric charge. An electron is negative, a positron is positive. And here's the thing, if you do Wu's experiment with antimatter, with anti-cobalt-60, you get the opposite result. The positrons come out in the opposite direction compared to where the electrons came out. So suppose you and your alien friend both do this experiment. You both report that the particles came out down relative to the spin. You think you've successfully communicated left and right. But if one of you is matter and the other is antimatter, you've actually got it backwards. When you finally meet up to shake hands and the alien sticks out what it thinks is its right hand, it might actually be extending its left hand. And that's not just awkward, that's dangerous. Because if you're made of matter and he's made of antimatter and you touch, you'll annihilate in a tremendous burst of energy. That handshake would be the last thing either of you does. Now, why does this happen? What is it about the weak force that makes it behave differently in a mirror? This is connected to something very deep about the nature of particles. You see, particles like electrons and neutrinos have a property called spin. They're spinning in a quantum mechanical sense. And this spin can be aligned with the direction the particle is moving, or against it. We call this handedness, or helicity, or chirality. Lots of fancy words for the same basic idea. Here's what's remarkable. The weak force doesn't treat left-handed particles the same way it treats right-handed particles. Neutrinos, these ghostly particles that barely interact with anything, come in only one-handedness. All neutrinos are left-handed. All antineutrinos are right-handed. The weak force is prejudiced. It has a favorite direction built into it. Now you might ask, why? Why should the universe be this way? And I have to tell you, we don't really know. We can describe it mathematically. We've built it into our theories. The standard model of particle physics includes this asymmetry. But as to why nature chose to be this way rather than some other way, that's a deeper question. It might be connected to why there's more matter than antimatter in the universe. It might be connected to the direction of time. There are theories, speculations, but we don't fully understand it. What we do know is this: the universe is not symmetric. It's close to symmetric. Most of the forces are symmetric. But at a fundamental level, built into the weak nuclear force, there's an asymmetry. The universe has a handedness. In a very real sense, the universe is made of mirrors, but they're not perfect mirrors. They're mirrors that can tell the difference between themselves and what they reflect. And there's more. In 1964, two physicists named James Cronin and Val Fitch discovered something even stranger. They found that even if you combine charge conjugation, swapping particles with antiparticles, with parity, swapping left with right, you still don't get perfect symmetry. There's a tiny effect where even doing both of these operations together doesn't quite give you back the same physics. This is called CP violation, and it's even more subtle. The only combination that seems to work perfectly is if you do three things together: swap charge, swap parity, and reverse time. That combination, CPT, seems to be an exact symmetry of nature. If you take any physical process, swap all particles with antiparticles, flip everything left to right, and run time backwards, you get a physical process that follows the same laws. But you need all three operations. 2 out of 3 isn't good enough. Why is this? Again, we're not completely sure. It's connected to the deep structure of quantum field theory, the mathematical framework we use to describe particles and forces. There are theorems that say CPT symmetry must hold if your theory obeys certain basic principles: locality, Lorentz invariance, and so on. But the physical reason, the intuitive reason why nature chose to be this way, that's still something we're working to understand. You see, this is what's so wonderful about physics. You start with something simple, a mirror, left and right, things anyone can understand. And you follow the logic, you do the experiments, and you discover that built into the deepest levels of reality is something unexpected. The universe has opinions about things we thought it wouldn't care about. It prefers one kind of spin over another. It treats matter slightly differently than antimatter. And every time we discover something like this, it opens up new questions. Why is there so much more matter than antimatter in the universe? If the weak force treats them slightly differently, could that have caused a tiny imbalance in the early universe that grew into the huge imbalance we see today, where everything is matter and there's almost no antimatter around? We think the answer is yes, but we're still working out the details. Or think about this. Life on Earth is chiral. The amino acids that make up proteins all have a particular handedness. They're left-handed. The sugars in DNA are right-handed. If you made a mirror image human being with right-handed amino acids and left-handed sugars, the chemistry wouldn't work. You couldn't eat regular food. Regular viruses couldn't infect you. You'd be biochemically incompatible with all life on Earth. Why did life choose one-handedness over the other? Was it just random chance early in the history of life? Or is it connected somehow to the fundamental asymmetry in the weak force? Could the slight preference the weak force has for one-handedness over another have somehow influenced the chemistry that led to life billions of years ago? We don't know, but it's a fascinating question. What I'm trying to tell you is that the universe is full of surprises. Things that seem obvious turn out not to be true. Symmetries that seem like they should hold turn out to be broken, and every broken symmetry tells us something new about how nature works. The mirror is not just a piece of silvered glass. It's a tool for thinking about the deep structure of reality. When you look in a mirror, you're seeing something that's almost, but not quite, the same as the real world. And that not quite is where some of the most interesting physics happens. So the next time you look in a mirror and wave at yourself, think about Wu's experiment. Think about those cobalt nuclei spinning in the cold, spitting out electrons preferentially in one direction. Think about the fact that the universe itself has a handedness, a sense of direction, built right into the fundamental forces. The universe is made of mirrors, imperfect mirrors, mirrors with a twist, mirrors that know the difference between left and right. And we're still learning what that means. We're still discovering what other secrets are hidden in that tiny asymmetry, that slight preference nature has for one direction over another. That's what makes physics so exciting. You start by trying to explain something simple to an alien, and you end up discovering something profound about the nature of reality itself. You find that the universe is stranger, more interesting, more subtle than you ever imagined. And there's always more to discover, always more to understand. The universe doesn't just reflect things, it selects things. It makes choices. It has preferences. And every time we discover one of these preferences, one of these asymmetries, we learn something new. we get a little closer to understanding how this remarkable universe of ours actually works. And that's wonderful. That's absolutely wonderful.